Imagine 10,000 servers, spread across 3 continents, no central coordinator, no leader. One of them dies, and within seconds, every other server knows it's gone. How? They didn't broadcast, they didn't check in with a master, nobody told them, and yet the news spread. They gossiped. This is how gossip protocols work. And once you see it, you'll spot it running underneath Cassandra, Consul, Redis Cluster, and half the infrastructure you touch every day. The simplest idea: every server pings every other server every second, heartbeats everywhere. With 10 nodes, that's 90 messages per round. Fine. With 100 nodes, that's 10,000. Still fine. With 10,000 nodes, that's 100 million heartbeats every single round. Your network melts before you finish provisioning the cluster. The cost grows as n squared, and n squared always wins eventually. So we need something smarter, something where each node talks to only a few peers per round. But still, somehow, the whole cluster stays informed. Here's the trick. Every second, each node picks 3 random peers and tells them everything it knows. That's it, that's the protocol. Say one node learns a new fact. Maybe that node 7 just died. Round 1, it tells 3 random peers. Now 4 nodes know. Round 2, each of those 4 tells 3 more. Now 16 know, roughly. Round 3, 64. Round 4, 256. Early on, the count roughly quadruples every round. The news spreads like a rumor through a town, or like an epidemic through a population. That's not a metaphor. Epidemiologists and distributed systems engineers use the same equations. Let's make the math explicit. If every informed node tells k random peers per round, the number of informed nodes roughly multiplies by k plus 1 each round. That's exponential growth. To saturate a cluster of n nodes, you need roughly log base k plus 1 of n rounds. For a million nodes at fanout 3, that's about 10 rounds, 10. Linear cost per node, logarithmic time to saturate, that's the magic trade. Each node does a tiny, constant amount of work per second, and in exchange, the cluster learns any new fact in logarithmic time. This is why gossip scales where broadcast doesn't. There isn't just one flavor of gossip, there are 3. Push: a node sends its latest state to a random peer. Fast when the news is fresh, because informed nodes keep spraying updates outward. Pull: a node asks a random peer, "What do you know?" Great later, when most of the cluster is already informed. Because every pull from an uninformed node is guaranteed to find fresh data. Push-pull: both nodes exchange state in a single round trip. You get the strengths of both styles, and this is what most real systems actually use. Push is a shout, pull is a question, push-pull is a handshake. Knowing a node exists is easy. Knowing a node is dead is hard. Network links drop packets. A lost ping doesn't mean the peer is gone. It might mean your cable is flaky. SWIM solves this. It's the failure detection protocol behind Consul and Serf. Node A pings node B no response after a timeout. A doesn't give up. Instead, A asks a handful of other random nodes, "Can you reach B?" Those nodes ping B on A's behalf. If any of them succeed, B is alive and the network was just flaky. Only if every indirect probe also fails does a mark B as suspect, and gossip that suspicion out across the cluster. If no one refutes it within a grace window, B is finally declared dead. One bad link can't kill a node. It takes consensus from several observers. 2 nodes gossip. They compare their views of the cluster. Their tables disagree. Which one wins? Every piece of state carries a version number, a monotonic counter that only goes up. When node A's table says node 5 is at version 12, and node B's table says node 5 is at version 15, B's version wins, every time. No locks, no coordination, no argument. The higher version is always correct by definition. Each node updates only its own row, so there's never a real conflict, just slightly stale views that catch up through gossip. This is why the protocol converges without a leader. Math, not authority, decides who's right. You have almost certainly touched gossip, probably without knowing it. Cassandra uses gossip for cluster membership. Every node learns who its peers are, their schema versions, their token ranges. No master directory. Consul and Serf, both built on the Swim variant we just saw. Service discovery for millions of servers, powered by little random conversations. Redis Cluster. Each shard gossips its view of the hash slot map. Clients learn the whole topology from any node. Even Bitcoin gossips. New transactions spread across the peer-to-peer network the same way. When a system is too big to coordinate and too important to go down, gossip is usually how it stays alive. Gossip is not free. You get eventual consistency, not strong consistency. When a fact enters the cluster, it takes logarithmic rounds to propagate. That's seconds, not milliseconds. If you need RAF-style agreement on a value right now, gossip is the wrong tool. You also pay a constant bandwidth tax. Every node gossips every second forever, even when nothing's changing. That keep-alive traffic is the price of staying ready. And detection is probabilistic. Pick too aggressive timeouts and you get false positives. Too relaxed, and failures take longer to catch. What you buy in exchange is robustness. No leader to lose, no single point of failure. A cluster that keeps converging even when machines, cables, and data centers are misbehaving. So here's the lesson hiding inside gossip protocols. A tiny, randomized peer-to-peer conversation, repeated every second, by every node, converges on cluster-wide truth. No leader, no central database, no coordination, just a few random whispers per round. And out of that randomness, you get something counterintuitive: robustness. A system that scales to thousands of nodes, tolerates widespread failures, and rebuilds its view of the world automatically. Randomness isn't a bug here, it's the engine. When coordination is too expensive and certainty is too slow, gossip wins. Thanks for watching. See you in the next one.